The seamless manufacturing process begins with a solid steel bar that is carefully selected based on its chemical composition and desired grade of pipe. The steel bar is cut into smaller sections called billets, which are then cut into specific lengths depending on the desired dimensions of the finished pipe. The billets are transferred one at a time to a rotary hearth furnace, where they are heated to approximately 1,300 degrees Celsius. The furnace floor rotates clockwise, ensuring uniform heating of the billets. Once heated, the billets are removed from the furnace and transported to the rotary piercer. At the rotary piercer, the solid round heated billet is converted into a hollow shell by cross-rolling over a high alloy piercing point. This cross-rolling action generates alternating tension and compression forces in the core of the billet, creating a void in the center as it comes into contact with the piercer point. The hollow shell formed at the piercer has a wall thickness that is further reduced to the final tolerance by longitudinal extrusion on the retained mandrel mill. The outside diameter is rolled down by a series of 7 reduction stands using a chrome-plated tool steel mandrel. This reduction in diameter converts the heavy wall thickness of the piercer hollow into length as it passes through the mill. After passing through the mill, a mill extractor decreases the tube's outside diameter further as it extracts the tube while the mandrel is withdrawn. The pipe then enters a wall thickness gauge, where it is scanned by 24 laser beams and 9 separate radiographic beams. These measurements provide precise outer diameter and wall thickness measurements over the length of the pipe. The tube is then transferred to a walking beam reheat furnace for reheating before it proceeds to the stretch reducing mill. The final outside dimension of the tube is calibrated on a 22 stand mill, where 3 rolls in each stand carefully stretch the tube to create the final outside diameter. The hot-rolled tube is discharged onto a cooling bed, where samples are cut and sent to the on-site lab for testing. Individual pipes are cooled to ambient temperature before their ends are cropped at the mill's cold saws. The pipes are then transported to the heat treatment line for quenching and tempering. In the heat treatment line, the pipes are heated to 870 degrees Celsius in a walking beam preheat and quench furnace. After reheating, the pipes pass through a water spray quench unit consisting of 7 spray quench heads with 800 individual water nozzles. The high-pressure water evenly applies the quench to the rotating pipe. Next, the pipe is transferred to a tempering furnace where it is preheated to 510 degrees Celsius and slowly cooled. This tempering process increases the pipe's ductility or toughness. Precise control of time and temperature during tempering is critical to achieving well-balanced mechanical properties in the finished pipe. After quenching and tempering, the pipe passes through a 3-stand resizing mill that calibrates the outside diameter to final tolerances. The pipe is then straightened on a rotary straightener while still hot. Samples are taken for testing of physical properties before the heat-treated and tempered pipe is transferred to a cooling bed and cooled to ambient temperature. The finishing process is a crucial step in the seamless steel production process. It involves various steps to ensure the pipe's dimensional accuracy, surface finish, and overall quality. First, the hollow shell formed at the piercer is further processed to reduce its wall thickness to the final tolerance. This is achieved through longitudinal extrusion on the retained mandrel mill. The pipe's outside diameter is rolled down using a series of reduction stands equipped with chrome-plated tool steel mandrels. These reduction stands gradually decrease the pipe's diameter, converting the heavy wall thickness of the piercer hollow into length. Next, the pipe enters a wall thickness gauge where it undergoes meticulous scanning. Laser beams and radiographic beams are used to measure the outer diameter and wall thickness of the pipe. These measurements are critical for maintaining the desired specifications and ensuring the pipe's quality. After passing through the wall thickness gauge, the pipe is transferred to a walking beam reheat furnace. The furnace reheats the pipe to a specific temperature before it proceeds to the stretch-reducing mill. The stretch-reducing mill consists of several stands equipped with rolls that carefully stretch the pipe to achieve the final outside diameter. This process ensures dimensional accuracy and smooth surface finish. Once the pipe has undergone the finishing process, it is ready for the final touch pipe varnish. Varnishing is the application of a protective coating to the outer surface of the pipe.
Raw material selection and quality testing. Armoson emphasizes the use of alloyed steel that meets world standards. Each batch of raw material undergoes rigorous quality testing to ensure it meets the required specifications. This step is crucial to maintain the high-quality standards of their pipes. Heating and shaping. The raw materials, in the form of billets, are heated until they reach a rubbery consistency. At this point, they undergo a complete physical shape change. This is a critical step in the production of seamless pipes, as it ensures that there are no seams or welds in the final product. Pipe drawing. The billets, after being heated and shaped, are drawn through the first and second pipe drawing units. Controlled cooling and reheating are performed during this process to maintain both the material's molecular structure and physical properties while shaping the material. This results in the seamless pipes with the desired thickness. Quality control. Throughout the production process, quality control measures are in place to ensure that the seamless pipes meet the required specifications and adhere to international standards. The energy industry continuously pushes the boundaries of technology and engineering to extract resources from the most challenging environments. Statoil ASA, a prominent player in the oil and gas sector, embarked on a groundbreaking project in the North Sea to develop a new oil field. One of the critical components of this endeavor is the transportation of crude oil to a refinery. This task necessitates the creation of a new pipeline, leading to the requirement of an innovative solution to connect to Statoil's refinery in Mongstad, Norway. The challenge at hand: the pipeline must traverse through extremely hard granite rocks, a feat that demanded the implementation of a horizontal directional drilling (HDD) process of unprecedented complexity. In this extraordinary venture, Statoil joined forces with Visser and Smith Hanab, VNSH, renowned for their expertise in complex directional drilling. Collaborating closely with the client and global experts, a formidable solution was devised to conquer the formidable granite rocks. Notably, Statoil and Sapem, in partnership with VNSH, engineered an offshore landing that would facilitate the installation of a substantial 92 centimeters oil pipeline. This pipeline would be pulled from a strategically positioned pipeline laying vessel stationed in Fens Fjord, ultimately connecting to the Mongstad refinery. The intricate nature of this task led Statoil to draw upon VNSH's experience in intricate directional drilling. The fact that VNSH had successfully executed a similar project at the same location in 2007 lent them a unique advantage. In March 2016, the contract between Statoil and VNSH was inked, marking the formal initiation of a process that demanded meticulous planning, innovative design, and precise execution. The timeline of this ambitious undertaking is a testament to the dedication required for such high-stakes endeavors. The project's designing and preparatory stages span the entirety of the summer following the contract signing. By August 2016, the groundwork was established, paving the way for operational commencement. In January 2017, the pilot drilling, with a diameter of 28 centimeters, was successfully accomplished. Subsequently, VNSH embarked on the initial reaming phase with a diameter of 71 centimeters. This gradual expansion of the drilling diameter was necessary to navigate the varying rock formations and layers that posed formidable challenges to predictions and strategic planning. The Mongstad project was marked by distinctive challenges that necessitated tailored solutions. The sheer difficulty of the task was encapsulated in the steep entry angle of 24.5 degrees and the depth of the exit point at an astonishing 315 meters below sea level. Standard operating conditions for the 250-ton HDD rig dictated a maximum entry angle of 20 degrees. This divergence prompted VNSH to conceptualize and install a steel frame construction, ingeniously overcoming the entry angle discrepancy. Delving into the depths of engineering complexity, the project faced the conundrum of operating at a depth where the pressure differentials were significant. The exit point's depth, residing at 315 meters below sea level, subjected the operation to water pressures of approximately 31 bars. Such intense pressure could lead to seawater intrusion into the borehole, resulting in cuttings flowing back and potentially obstructing the hole or even jamming the equipment. VNSH devised an ingenious solution involving the installation of two massive seawater pumps, intricately interconnected through extensive piping. This system was designed to effectively flush out the cuttings from the borehole. Traditional methods for clearing boreholes proved impractical due to the exceptional water depth. The operational strategy adopted by VNSH involved the gradual enlargement of the original hole through forward reaming conducted in three distinct stages. The diameters targeted for reaming were 71 centimeters, 97 centimeters, and 122 centimeters, sequentially. This meticulous process paved the way for the final installation of the 92 centimeters oil pipeline. The responsibility for this crucial installation lay with Sapem, commissioned by Statoil. Undoubtedly, the Mongstad project etches its mark as a global pinnacle of technical innovation. The parameters of this undertaking were staggering, encompassing the need to navigate through exceptionally hard granite rocks with an initial strength of 250 megapascals, MPa, coupled with forward reaming activities expanding to an impressive diameter of 122 centimeters, all while spanning a total length of 800 meters. This project transcends the boundaries of conventional engineering challenges. Remarkably, even the choice of drill pipes underwent thorough evaluation and innovative engineering. Although VNSH typically employed 7 5/8 drill pipes for their operations, the unique conditions of the Mongstad project necessitated a rethinking of this approach. The engineers at VNSH, in collaboration with global experts and the client, devised a robust solution to address potential issues of buckling and metal fatigue in these pipes. Through thick and thin, the team operating in the rugged Norwegian terrain and unpredictable climate demonstrated exemplary dedication and tenacity. Every obstacle was met head-on, and challenges were approached with a positive spirit. The successful execution of the Mongstad project stands not only as a triumph in engineering innovation, but also as a testament to the power of collaboration, expertise, and sheer determination in conquering the most demanding frontiers of human endeavor. CP Technologies' involvement in the Santa Lucia Tunnel project began with the design and manufacturing of key components. Within an impressive time frame of just 6 months, CP Technology completed the construction of a steel-framed building, the development of lifting and handling equipment, and the centerpiece of the operation, the carousel plant. This comprehensive approach to in-house production sets the stage for a highly coordinated and efficient tunnel segment manufacturing process. One of the foundational aspects of this production process is the meticulous design of segment molds. Advanced 3D design tools are employed by the engineering team to craft these molds, ensuring not only precision but also immediate structural verification of the assembly. This design phase is critical, as it sets the stage for the subsequent stages of production. Once the molds are designed, specialist engineers take charge of ensuring strict adherence to manufacturing tolerances. The use of 3D controls throughout the entire production process guarantees that each segment meets the exacting standards required for tunnel construction. This meticulous attention to detail is vital to ensure the integrity and safety of the tunnel. The production process also involves the design and implementation of hydraulic systems tailored to the client's specifications. These systems play a crucial role in the manipulation and formation of tunnel segments, further emphasizing the tailor-made approach taken by CP Technology to meet specific project requirements. CP Technology has embraced the principles of Factory 4.0, with a focus on minimizing costs and production time while enhancing safety and traceability. This forward-looking approach leverages cutting-edge technology to streamline operations, reduce waste, and optimize resource utilization. In doing so, it not only contributes to the efficiency of the production process, but also positions the company at the forefront of industry innovation. To ensure the quality of the tunnel segments, concrete vibration is utilized during the casting process. Proper vibration is fundamental for achieving a flawless concrete finish and maximizing the amount of concrete that fills the mold during casting. CP Technology offers various vibration options, including electric with inverters or pneumatic vibration, allowing for flexibility in meeting specific project requirements. Safety is paramount in the tunnel segment production process. CP Technology has implemented various safety features to protect workers and ensure smooth operations. One notable innovation is the shutter opening system, which is integrated into the mold. This system not only saves time but also enhances safety, reducing the risk of accidents and improving efficiency. The inclusion of remote control systems, operated via smartphones or PCs, allows for real-time monitoring of production and the prompt resolution of any issues. This proactive approach to safety management ensures that potential faults are addressed as soon as they occur, minimizing downtime and delays. The integrated segments tilting device is a pivotal element in the process. It facilitates the demolding, tilting, and transportation of segments to a pre-storage area efficiently. Safety brackets are activated during the lifting of segments, ensuring secure handling and reducing the risk of damage. Automatic positioning systems further enhance safety and precision by ensuring perfect alignment in both horizontal and vertical planes. This streamlined approach eliminates the need for intermediate steps, minimizing the risk of damage to segments and reducing the overall stress induced during handling. Research by renowned universities has validated the effectiveness of this system, particularly for large and slender segments. For efficient handling and management of segments, an integrated video control system is employed. This system allows a single operator to oversee the handling of segments to the pre-storage area, improving safety conditions and cost effectiveness. The combination of advanced technology and thoughtful design considerations underscores CP Technologies' commitment to safety and efficiency. With 3 decades of experience in precasting systems and a strong culture of innovation, CP Technology stands as a unique partner in the market, capable of delivering turnkey prefabrication plants with precision. Each step of the production process is subject to rigorous quality checks, ensuring that the final product meets the highest standards of excellence.
The construction of a pier involves several crucial steps to ensure its structural integrity and durability. From rebar fabrication to concrete pouring, each phase contributes to the overall strength and stability of the pier. The first step in the manufacturing process of a pier is the fabrication of reinforcing bars, commonly known as rebars. Rebars are essential components that provide tensile strength to the concrete structure. They are typically made of steel and come in various sizes and shapes, depending on the design requirements. During the rebar fabrication process, steel rods are cut, bent, and assembled according to the specified design and dimensions. This process is usually carried out in a dedicated fabrication shop equipped with specialized machinery. The rebars are bent using automated bending machines, ensuring accuracy and consistency in their shape and dimensions. Once the rebar fabrication is completed, the construction crew proceeds to the site and initiates the excavation process. Excavation is a crucial step in the construction of a pier, as it involves the removal of soil to create a hole or trench where the pier will be built. The dimensions and depth of the excavation are determined by the design specifications and considerations of the surrounding soil. Excavation can be accomplished using various types of equipment, depending on the scale and nature of the project. Heavy machinery such as excavators, backhoes, or other earth-moving equipment are commonly utilized. These machines have the capability to dig through the soil, remove it efficiently, and shape the excavation area according to the design requirements. During the excavation process, the soil that is removed is either stockpiled for future use or disposed of if it is deemed unsuitable for backfilling. If the soil is suitable for reuse, it may be stockpiled nearby for later use in backfilling or landscaping. This can help minimize waste and reduce the need for additional materials. The rebars are carefully placed in accordance with the design specifications, ensuring that they are aligned correctly and positioned at the required depths. Supports or chairs are used to hold the rebars in place and maintain their proper positioning during the concrete pouring process. These supports or chairs prevent the rebars from sinking or shifting while the concrete is being poured. Proper installation of the rebars is of utmost importance for the structural strength of the pier. The rebars provide reinforcement to the concrete, enhancing its ability to withstand tensile forces. By distributing the tensile stresses throughout the structure, the rebars help prevent cracking or failure in the pier. During the installation process, close attention is paid to the alignment and spacing of the rebars. This ensures that the reinforcement is optimally distributed throughout the pier, providing uniform strength and durability. Any deviations from the design specifications are addressed and corrected to maintain the structural integrity of the pier. For specific projects or larger diameter rebars, welded splices may be utilized. Welded splices involve the fusion of rebars using welding techniques, creating a durable and permanent connection. The choice of rebar splicing method depends on various factors, including design requirements, load considerations, construction schedule, and cost effectiveness. Proper rebar splicing ensures that the rebars function as a unified unit, providing the necessary reinforcement throughout the entire height of the pier. It maintains the integrity and structural strength of the pier, allowing the rebars to work together in resisting applied loads and preventing potential failure points. Quality control measures are implemented during the splicing process to verify the integrity of the splices. Inspections and tests may be conducted to assess mechanical properties such as tensile strength and load-carrying capacity. These measures ensure that the spliced rebars meet the required standards and will perform reliably throughout the pier's lifespan. Before the concrete pouring takes place, it is essential to conduct concrete testing to ensure its quality and properties. Concrete testing involves taking samples from the freshly mixed concrete and subjecting them to various tests in a laboratory. Some of the common tests conducted on concrete samples include compressive strength testing, slump testing, and air content testing. These tests provide valuable information about the concrete strength, workability, and durability, helping to ensure that it meets the required standards and specifications. Once the concrete has undergone testing and received approval, the final step in the manufacturing process of a pier is to pour it into the excavated area. Concrete pouring requires careful coordination and expertise to ensure the uniform distribution and proper consolidation of the concrete throughout the pier. To begin the pouring process, the concrete is transported to the construction site using specialized vehicles such as concrete mixers or pump trucks. Concrete mixers are commonly used for smaller projects, where the concrete is mixed on site and transported to the pouring location. Pump trucks, on the other hand, are employed for larger projects and allow for the direct pumping of concrete from the truck to the pour site, which can be particularly beneficial for projects with restricted access. Once the concrete reaches the pour site, it is discharged into the excavated area. This is typically achieved through the use of chutes, conveyors, or pumping systems, depending on the site conditions and the accessibility of the area. The concrete is carefully guided and directed to ensure it is evenly distributed throughout the pier. During the pouring process, it is crucial to maintain a consistent flow rate and avoid interruptions or delays that could lead to cold joints or weak points in the concrete. The concrete must be properly consolidated to eliminate any voids or air pockets. This can be achieved using vibrators or other consolidation techniques, which help to ensure that the concrete is dense and free of any potential weaknesses. In addition to proper consolidation, attention is given to the finishing of the concrete surface. Finishing techniques, such as screeding, floating, and trowel welding, are employed to achieve the desired smoothness, texture, and levelness of the exposed concrete surface. After the concrete has been poured and finished, it undergoes a curing process to allow it to gain strength and achieve its intended properties. Throughout the pouring process, strict quality control measures are implemented to ensure the adherence to design specifications and construction standards. Proper concrete pouring is crucial for the overall structural integrity and longevity of the pier. It ensures that the concrete is evenly distributed, consolidated, and finished to provide the necessary strength, durability, and aesthetic qualities required for the project. Basement excavation using bored pile technique involves several steps to ensure a stable foundation for tall buildings or industrial complexes. This method is preferred when dealing with unstable or difficult soil conditions, and it produces less noise and vibration compared to conventional methods. The surveyor locates the excavation point based on approval drawings using a theodolite or kyoto light. These instruments help calculate angles, horizontal distance, and fix the precise point. In the process of basement excavation using bored pile technique, one of the initial steps is to drill a primary hole to a certain depth. This is achieved using an auger pulpit machine, which is specifically designed for this purpose. The primary hole is typically drilled to a depth ranging from 20 to 30 meters, depending on the specific requirements of the project. Once the primary hole is drilled, a temporary steel casing is inserted into the borehole. The steel casing serves as a protective barrier to prevent the collapse of the surrounding soil during the excavation process. The diameter of the steel casing is typically 16 meters, providing enough space for subsequent steps of the bored pile construction. To ensure the vertical accuracy of the steel casing, it is crucial to check its alignment during the installation process. This is done using a plomb-bob, a weighted object suspended from a string. During the insertion of the steel casing, vibrating hammer is used. The vibrating hammer is a mechanical device that applies rapid vertical vibrations to the steel casing. The temporary steel casing provides temporary stability to the borehole during subsequent stages of the bored pile construction. It acts as a support for the surrounding soil and prevents any collapse or displacement that could compromise the integrity of the excavation. After the steel casing is in place, the hole is drilled further using a bucket to reach the required depth, which usually extends to the hard layer of soil. Simultaneously, polymeric slurry is pumped into the hole. The polymeric slurry serves two purposes. It applies continuous pressure to the surrounding soil to prevent cave-ins, and it helps in the removal of soil during drilling. The excavated soil is disposed of off-site using trucks. Once the excavation hole has reached the desired depth, typically around 12 meters, a reinforcement steel cage is carefully inserted into the borehole. The steel cage is constructed using a combination of vertical and horizontal steel bars that are interconnected to form a rigid structure. The steel cage serves multiple purposes in the bored pile construction. Firstly, it enhances the structural integrity and load-bearing capacity of the pile by providing reinforcement against bending and shearing forces. To ensure that the steel cage remains in position throughout the subsequent steps, it is welded to the temporary steel casing. This welding process securely attaches the cage to the casing, preventing any movement or displacement during the pouring of concrete and the removal of the casing. The welded connection between the steel cage and the steel casing is essential to maintain the alignment and integrity of the bored pile. It ensures that the reinforcement remains in the correct position, allowing for the efficient transfer of loads from the superstructure to the foundation. By welding the steel cage to the steel casing, the construction team can ensure the stability and integrity of the reinforcement system, which is vital for the long-term performance and strength of the bored pile foundation. After the reinforcement cage is in place, a tremie pipe is used to pour concrete into the borehole from bottom to top. The pressure from the polymeric slurry forces the excess slurry to go upwards. The concrete fills the borehole, and as it hardens, it provides the necessary strength and stability to the foundation. During the concrete pouring process, the steel casing is removed, and the excess polymeric slurry is taken away by pumping for reuse in subsequent boring processes. Once the concrete has set, the tremie pipe and steel casing are removed. The steel casing can be reused in future excavations. The borehole is backfilled with the excavated soil, and the site is cleared and cleaned. Spirals are a crucial component of pile rebar cages as they provide additional reinforcement and enhance the structural integrity of the pile. The spiral making process is the first step in the manufacturing process and involves the use of specialized machinery to create tightly wound spirals from continuous steel bars. To begin the spiral making process, a continuous steel bar is fed into the specialized machinery. The machine consists of a mandrel, which acts as a central support for the steel bar. The mandrel's diameter is determined by the desired dimensions and specifications of the spiral. As the machinery starts, the steel bar is gradually and uniformly wrapped around the mandrel. The machine controls the rotation, speed and pitch of the spiral, ensuring precision and accuracy in its dimensions. The pitch refers to the distance between successive turns of the spiral. This control mechanism allows for consistent and standardized production of spirals. The continuous rotation of the mandrel and the controlled movement of the steel bar result in a tightly wound spiral with closely spaced turns. The machinery's design and operation ensure that the spiral is securely formed and maintains its shape throughout the process. During the spiral making process, it is essential to monitor the quality of the spirals being produced. Inspections are carried out to check for any defects, such as irregularities in the spiral shape or improper dimensions. Any discrepancies are promptly addressed to ensure the production of high-quality spirals. Stiffeners are critical elements that add rigidity and strength to the pile rebar cage. In the manufacturing process, steel bars are cut to the appropriate lengths using cutting machines. These bars are then subjected to bending and shaping using hydraulic or mechanical benders, forming the desired configurations for the stiffeners. The bending process ensures that the stiffeners fit seamlessly within the rebar cage structure. To create a robust cage, the stiffeners are typically welded or tied to the main reinforcement bars, reinforcing the overall stability and load-bearing capacity of the pile. Cover blocks play a crucial role in pile rebar cage fabrication by maintaining the desired concrete cover over the reinforcement bars. These blocks serve multiple purposes, including protecting the steel bars from corrosion, providing insulation against fire, and contributing to the overall structural strength of the pile. The cover block manufacturing process begins with the use of molds that are designed to create blocks of specific dimensions. The molds can be made of metal, plastic, or other suitable materials. The dimensions of the molds are determined based on the required cover thickness and the size of the reinforcement bars. To create the cover blocks, concrete or composite materials are poured into the molds. The concrete mix used for cover blocks is typically formulated to provide adequate strength and durability. Special attention is given to the composition to ensure that the cover blocks exhibit the necessary properties for their intended use. The rebar cage making process is a critical step in pile rebar cage fabrication. It involves the assembly of all the individual components, including spirals, stiffeners, and main reinforcement bars, to create a robust and structurally sound cage. To begin the rebar cage fabrication, the main reinforcement bars are placed on the assembly table in the desired configuration. The bars are carefully positioned and aligned according to the engineering specifications and design requirements. The placement of the bars ensures that they will effectively distribute loads and provide the necessary strength to the pile. Next, the spirals and stiffeners are added to the assembly. Spirals, which were made separately in the earlier stage, are positioned at predetermined intervals along the length of the cage. These spirals wrap around the main reinforcement bars, providing additional reinforcement and enhancing the cage's overall structural integrity. Stiffeners, which were manufactured by cutting and shaping steel bars, are placed in the desired locations along the cage. Stiffeners add rigidity and strength to the cage, preventing deformation and enhancing its load-bearing capacity. They are typically positioned perpendicular to the main reinforcement bars and secured in place. The components of the rebar cage, including the main reinforcement bars, spirals, and stiffeners are securely connected to each other. This is typically done through two methods: welding and tying using steel wire. Welding involves using electric arc or gas welding techniques to fuse the individual components together. Welding ensures a strong and permanent connection between the bars, spirals, and stiffeners. Skilled welders carefully perform the welding process, ensuring proper penetration and adherence to welding standards. Alternatively, tying using steel wire can be employed to connect the components. Steel wire is wrapped around the intersecting bars, spirals, and stiffeners, creating a tight connection. This method requires expertise in tying techniques to ensure that the connections are secure and provide sufficient reinforcement. Throughout the rebar cage making process, quality control measures are implemented. Inspections are conducted to verify the correct placement of components, adherence to design specifications, and the integrity of connections. Any defects or issues identified during the inspection process are rectified to ensure the production of high-quality and reliable rebar cages. Once the rebar cage fabrication is completed, the cage is carefully handled and transferred to the rebar cage stock area for storage. This area is dedicated to organizing and storing the fabricated cages until they are ready for transportation to the construction site. Once the rebar cages are ready to be transported to the construction site, they are loaded onto trailers. This step requires specialized equipment such as cranes or forklifts to lift and position the cages onto the trailers. Care is taken to ensure proper weight distribution and secure fastening to avoid any movement or damage during transit. The cages are then transported to the construction site using trucks or trailers, ready for installation. The manufacturing process of pile rebar cage fabrication involves several meticulous steps that ensure the production of high-quality reinforcement cages.